So far, we have seen hypothesis testing considering only two variables at a time, but often we need to test models that include multiple variables. The most common technique for this purpose is regression, which is aimed at testing the effect of multiple independent variables, usually called x, on a common dependent variable y. X variables can be either continuous or categorical, while y needs to be continuous. For example, in the IPS project, we wanted to test the impact of various purchasing practices, such as supplier assessment, supplier collaboration, and supply-based redesign on purchasing performance. In this way, we can test multiple relationships simultaneously, thus obtaining more solid results, since we take into consideration all possibly relevant variables. Regression allows also to introduce the so-called control variables, that are variables that are not included in our hypothesis, but could have some relationship with the y, and so we want to clean out their effect. In the IPS project, the typical control variables are company industry, country, and size. Usually, we assume a linear relationship between y and x, but also more complex forms are possible. We often consider regression a way to test causality, but actually regression does not provide a proof of causality per se. It is our theory that supports the assumption that x is the cause and y the effect, not the statistics per se. How can we interpret the output of regression analysis? We need to look essentially at two types of information. First of all, we look at the R-squared, which is a measure of the overall goodness of the model. R-squared tells us the percentage of the variance of the dependent variable that is explained by the independent ones, so the higher, the better. Then we need to look at the coefficient of the independent variables, the betas, to check if they are significantly different from zero by looking at the p-value as usual, and in case they are significant, we are interested in their sign and magnitude. In case the dependent variable is not continuous, we cannot use linear regression, but we should use appropriate techniques. If the dependent variable is dichotomous, that is binary, such as 0 or 1, true or false, the appropriate technique is binary regression, usually adopting the logit or probit model. For example, if our dependent variable is the result of an exam, pass or fail, and we want to analyze if this is affected by the percentage of classes attended, the number of study hours, and the number of failed attempts, we can use this technique. If the dependent variable is multidichotomous, that is consisting of multiple categories, such as local, regional, and global, the appropriate technique is called multiple discriminant analysis. We use it to predict the likelihood that a respondent will belong to a particular class or group based on several independent variables. For example, we may want to test if company size, industry, and country are related to the categorization into local, regional, global. Another quite popular technique today is structural equation modeling, SEM, which combines together a confirmatory factor analysis, CFA, and a sort of regression model among latent factors. This technique allows to test simultaneously the measurement model, that is the factor analysis, and the structural model, that is the regression part. SEM is powerful because it provides the overall goodness of fit of the entire model together with the values and significance of all the coefficients. But for this reason, it is also very demanding in terms of sample size. Finally, another useful multivariate technique is cluster analysis. If we need to identify groups of respondents that share common characteristics, cluster analysis is what we should use. This is the typical case of marketing analysis, in which we need to identify market segments that are groups of customers that are similar among them in terms of demographics, preferences, interests, and so on. To run cluster analysis, we need to select a number of metric variables, or factors, that we want to use to classify our respondents. For example, company size, spending, strategy, and so on. Then, cluster analysis will measure the distance of each respondent from the others on the basis of the values of the chosen set of variables, and join together in the same cluster those respondents that are closer to each other, while separating them from those that are far away. The key results of cluster analysis are the identification of the best number of clusters and assigning each respondent to a cluster. At the end, we will be able to define the characteristics of each cluster by calculating its center, that is the average values of our clustering variables for the companies included in the cluster.